Okay, so this is a quick GUI for this offset measurement tool, Disp Calc Bethy version 1. So in order to start it, just open MATLAB and then go into the correct folder and type the name of the tool. And then just enter. If you do so, you'll see this GUI opening up. As you can see, it contains a number of boxes. This is box 1, 2, 3, and 4. And that's basically also outlining the workflow. The workflow itself is also highlighted by the color coding. So now you can see only load DM is actually green, so you can actually use it. All the other buttons are basically red, so that means they're not active right now. That helps you to get the workflow organized. So we'll just go through one example on how to measure an offset with this tool. The tool itself is for, just to say that, is for lateral displacements, but also for vertical ones. They are measured independently, so if you want to measure only vertical, you can basically follow the same steps, and in that case just ignore the lateral measurements that are produced, or vice versa, if you're interested only in lateral displacements. So for now, let's just load a DM without any averaging, any smoothing. So just press the button and look for the location of the DM. It's going to be an ASCII file, as it is provided by ArcGIS or Esri. Just open it, and you can see some information here about the cell size, etc. It's successfully loaded, so press here, and then you can plot an overview. This overview plot uses a hillshade plot, and the hillshade parameters that are used are shown in here. So when I press, it would generate an overview. This is the data that I just loaded. If I don't like this representation, you can just play with these values. For example, change in z-factor, plot again, and you can see you have more contrast. The next step is that you will do in this measurement approach is define a zoom box. That's basically the idea, is that you can process or first import large data sets without doing all the calculations and backslipping on the whole data set, because that can be a bit intense computationally. So next thing, as I said, is define a zoom box, and that's basically what you do. Let's just zoom in actually here first, is to define the area where you can see an offset. So here I want to measure this offset here, this feature, so I define a zoom box around it. So I just click this button once, and then in here click upper left and lower right corner. That's like that, just to have the actual feature somewhere centered in it. Once this is done, you can go to plot zoom and get a different representation of only this box, and all the other measurements are done on this subset of data. So if you don't like this representation, if you want to do other plots, you can change all the options right here. What this basically reads as drape topography with transparency, this value goes from 0 to 1, and color map, in this case topo, over the underlying other dataset. So here, let's say I want to do a slope map, and just plot again, so you can see slope now. I can invert the color maps with these buttons, and you can also change the values themselves. So here, maximum and minimum for slope is 0 to 60 degrees. So let's say my maximum is going to be 45, and you can get a bit more sharpness. Something I think really is important is to use contours. So here you have the contours, the maximum and minimum value of elevation, and in here you can then define the contour interval. Let's say make it 50 meters in that case, and here you can see the contours. I think in this I might actually use 20. Yeah, that's better. You just want to pick a value that gives enough detail without cluttering the overall figure. If you have done that, the next step, if you're happy with the representation of your DM, and if you can well visualize the feature that you want to reconstruct, in this case I want to reconstruct backslip this feature, or basically measure the displacement of this feature. If you like the visualization, then you can go to the next step, which is here. first define a fault trace, and you do that a number of times, and the number of times you do it is written right here. So 10 times. That's done because all the sampling that comes later is using these values and using the number of features that are traced, or the number of times it's traced, to generate a PDF basically. And the more you do it, the more accurate it's going to be. So 10 is just a compromise in that case. So I press this button here, this one, and now I have to trace this feature 10 times. In this case, the fault trace. The fault runs right here. So I'm going from here to somewhere here. And the only point that you have to make is really another point, but just click left twice. It doesn't matter whether these points can also be here and here. They don't have to be centered on the offset feature. Just the line itself, the vector has to be this more or less the one of the fault trace. And of course, you try to be as precise as possible with this measurement. However, that said, I'm doing this 10 times in this particular case to account for the fact that I probably don't get the perfect straight line every time. And so I just do it multiple times to get some probabilistic estimates here. So I just did that 10 times. And now next step is to, whoops, you can see here how many times I traced. Next thing would be to trace the actual feature. So one is called red, one is blue, just for representation. What you do for the tracing is you click with a mouse the features. I want to do this portion here, and first you just click. I want to do a left click to digitize it. You could basically do all kinds of things, and let's say this is of course completely wrong, so you just right click and these points will disappear again. You can do that all the way to remove everything. So I just click again, and what you try to do is basically to trace this feature that you have all the way up to the point that you say up to here, for example, I'm confident that this is the original shape. And then you trace into the fault. So if you know the fault is roughly in this area here, and you say, okay, where do you think the next line should go? How does it project into the fault? So let's say it's good, might be here or so. In order to mark that point, you then press F for the fault. Done. So you do that 10 times in this particular case also because it's taking this value as well. So as I said, you try to do this tracing in a way that you are getting as close as possible and to the overprinted portion. So let's see. This is a bit tedious, of course, and that's why it's probably you should probably do more than 10, but for this example at least I think that will be enough. And you can see I'm not doing exactly the same thing every time, but that's also the whole idea of this approach, to be precise but to acknowledge that my tracing cannot be, it's not unique, basically, that there's uncertainty in it. Almost done, I think. Yeah, so as you can see, my understanding is that all the way up to here I really do have the original shape of that feature, and here there's some overprinting happening, or something. The original shape of that channel of this feature is actually modified, so that's why I'm taking this part as original shape. Let's see. Okay, that's it. So now do the same thing for the other section. Just gonna click away. Okay, let's see, roughly here. So it's always left click, left click, left click, and the F button for fault. So roughly here or so, then projecting. Almost done. I think this is the last one. I didn't count. Okay. Yep. So now you can plot the traces. This is quite interesting because it tells you now, it shows you how well your line work was. So you can see here the points I've made for the fault trace, those ones here, the red ones and how they project into the fault here, and the blue ones and how they project in. And this is the longitudinal profile. So here it's basically taking the swath here around these mean line, around these lines I mean. In this particular case, it's a 100-meter box around this over here, and the same here. So that's where you get these longitudinal profiles, starting here, going up. So that's from here to here. And you can see there's different color coding, so the gray points on both sides are the ones that are the part from the projected sections. And this 0 here is the fault line itself. So this is distance from fault, basically here to here. Yeah. So that done is now we can and have to do two more things. We have to trace the longitudinal profiles, and that's done here. So next thing, you trace as before, just click twice. In this case, I'm taking the bottom here. Just click it twice, and then it projects into the fault. Okay, and this is also going to happen 10 times. I'm going to be quick to make this video not extremely long and boring. And almost done. Okay, done. And now doing the same thing for the other section. And right now I'm just clicking away. You have to, of course, really make sure that you have a feeling for what the actual pre-earthquake morphology was. And I'm not taking too much care of this right now, as you may have seen or realized. I'm a bit quick. Okay, done. So now we can plot the actual results. That's all the measurements that we do. You can plot the results. You get two PDFs, one for vertical and one for horizontal. So vertical is here and horizontal is here. And what you can do now is basically put these values in here. So my optimal horizontal displacement that I get from my tracing is about 900 meters. So I put 900 meters here, and for the vertical it is about 30 meters. Let's say, so I put these values in here, and then I can backslip. You'll see in a second how this looks like. You have two options. You can do this in 2D and in 3D. First I want to show 2D. So now you can see the backslipped longitudinal here. So just to show you what this means now, it's basically I was tracing here all the way, all the time, and then also on this axis. And if you connect them now, you might get the impression that they are somewhat continuous. I just draw this line from here to show that. It's not perfect, but I wasn't planning or, aiming to do a perfect job right now. Just for just to give you a feeling how this looks like. And here's the same thing for the map view, for the vertical, for the lateral displacement. So it looks pretty good. You can also do this in 3D, as I said. So you just click here and rerun, and you'll see. Now this looks the same, and this also looks the same, but you can now go here and rotate. Make this bigger. Get a nice view. So I think this measurement was actually quite decent. You can see this shape really looks nice now. Really well constructed. Yeah. Okay. So if you have done all that, you can then, let's reset. Okay. What you can do in the end is then go here and save. So in this particular case, this is UTM zone 8, so I just put 8. You can put a reference, you can describe the feature in here, and then you just press the save button and it will generate all the required outputs. Okay, let's do that. This is offset example. I'll just give it some name and then save. And it will open a lot of figures. Basically, it creates a lot of plots, a website at the same time, some KMZ files for overview, and eventually it will be all done. And hopefully there will be some text telling you that it's all done. Now it's doing the backslipping with the optimum and the 2 sigma values, and yeah, I'm almost done. So I'm looking here right now to see if this is finished. Okay, let's see. Yep, I'm done. So now let's see. I want to go just briefly to my folders. Where is it? It's my codes, offset market tools here, and now you can see here all the files that were created all the way from here to here. It's quite a few, so normally you would put them all in a different folder. Just for to show how this looks, you can then go to this HTML file, and then you can see here's the information. Here's some distance I didn't put in, the offset measurements, and here's the original, the traced, the tracing, the PDFs, and the backslip images. So that's, you have a full website. At the same time, you can then also look, so the figures are in here. You can also look at KMZ files. You'll also notice that there's a backslipped ASCII file now. This is the DM of the backslipped, optimal backslipped representation. So that's basically all I had to say. I think there are quite a number of things you can play with in terms of visualization options. One more thing. If you want to know measure a new feature, all you have to do is press this define zoom box again, and then say you want to now do, I don't know, maybe some feature here. That resets all your previous measurements, so you don't have to load everything again, and you can basically then start from again all the way. So you can see all this information is gone. It's all red now, and then basically it means that you have to redo it. So whenever you press this define zoom box, you'll reset your measurement and you say start from scratch. Okay.